Okay, here we go. Section 4.3 is on page 205 where it begins. It's a little bit lengthy. Extremely important. So try to stay with me. A lot of this we've already done. I've already taught you the first derivative test, and that's the very first thing you see on page 205. Well, other than the title, which is connecting the first derivative and the second derivative with the graph of the original. That's what we're out to do today. Connecting them together, okay? The first derivative test, in case you're wondering that we didn't actually call it the first derivative test. First derivative test is when you make a sign chart and try to decide if I got this going on or if I got this going on. Max or min, or maybe neither one. Have any of you done any exercises yet where you hit a shelf point at a critical value? Where the sign did not change as you jumped across it? That will happen to you today on the exercises. So critical values are where the first derivative is undefined or equal to 0. You list them all, put them all on a number line, and then you check on either side of them. And if there's a change in sign, you've got a max or a min. If there is no change in sign, you've got a shelf point or a vertical tangent, one of the two. But critical values give you a place to look for maxes and mins, right? Okay. All right. At the bottom, just to remind you how these things can occur, on page 205 at the bottom, it shows you two ways you could find a local max. The first one occurs where the derivative would be 0 because it's a nice smooth change from going up to going down. The other one would be a place that's undefined. When I say it, I mean the first derivative, because we have a corner or a cusp there, means that was a place, that was a critical value that was where it was undefined, but there's still a local max there because there's a change in the slope, the sign of the slope. Turn the page. Same thing for a local min, where it's undefined and also where it's equal to 0. There's examples of those. The next one is an example of a shelf point and also a kind of a hiccup there, but you can see that on both sides of that corner on number 3 that they're talking about, on both sides of that sharp corner right there, the slope is negative. And so there's no max or min there, but there's something going on. You can also have maxes and mins at endpoints. That's what, at the left endpoint and the right endpoint, if there's nothing else beyond there, you can have maxes and mins there. If there's nothing else bigger or smaller than that in the neighborhood. So you may want to refer back to this chart. I don't know. We've seen all of that already. So take a look at example 1. It says, using the first derivative test, it says for each of the following functions, use the first derivative test to locate the extreme values and identify any absolute extrema. So look at what he does. Find the author I'm talking about. On top of page 207 is the first time we've seen him draw a sign chart. But we've been doing it for quite a while. Okay, so what we would do is, as he shows you in the solution there, we got the first one's just a plain old polynomial. It's not a big deal. Third-degree polynomial. And he finds the derivative, sets it equal to 0, and finds that there are critical values at 2 and -2. So he puts those on a number line and shows that there's a sign change for both. And the first one, because it was positive first and negative second, is the maximum, and then vice versa. On the next one, which isn't quite so easy because it's got a polynomial combined with a transcendental. If you look down to the bottom of page 206, part B right there, we've got an e to the x combined with a polynomial right there. That's not quite so easy, but still we can take a derivative using the product rule. Remember that. Find the derivative, set it equal to 0, and we find that there are critical values at 1 and -3 if you do that. And again, we got sign changes. So those were really nice, neat first derivative test problems. The maximum on, just as a note, the maximum on that second one that's in the negative side is not so obvious graphically. You may miss it if you just graph it, especially on a standard screen, because it looks kind of flat there. So a first derivative test is kind of essential because sometimes the maxes and mins are not really, really obvious. So it's a good idea that you do the actual math. Okay, now we're going to get to the new stuff. I'll talk about the second derivative. And the second derivative is not about maxes and mins at critical values. The second derivative is about changes in concavity, concaveness. Those of you who just came in, we're on page 207. Near the bottom. The title of the discussion is concavity. Okay. Take a look at the graph just to the left as I read this, and pay special attention to the all the little flared out red tangent lines that are being drawn as it goes up. It says, as you can see in this figure, the function y equals x cubed rises as x increases. But the portions defined on the interval from negative infinity to 0 and the ones from 0 to infinity as we cross the origin turn in a different way. I'll call them terms. Okay, let me go back just for a second there. This is x cubed that we're looking at here, and it constantly increases. On every interval you want to choose, it is increasing. You go, not at 0. Remember, we don't increase or decrease on an interval. At a point, according to the author. This thing is always increasing. There is a shelf point at 0. It would produce a critical value. The derivative would. If you take the derivative, you get 3x squared. You set that equal to 0, you get x equals 0. And there is a critical value there, but it is not a max or min. It's a shelf point. But to the left of the origin and to the right of the origin, this curve turns differently. It's not a very great description, but you can see that they turn differently. Okay. Looking at tangents, we scan from left to right. We see that the slope y prime of the curve decreases. Now think about that. The slope, which is y prime, on the curve decreases. The slope gets smaller as you approach 0 to the left. You see that? Or you understand what I'm saying? The slope gets smaller. We approach 0 from the left side of 0. And it gets bigger as we move away from 0 on the right. The slope. So the slope decreases headed towards 0 from the left, and then after we pass that, it increases as we go to the right. And that's a very strange phrase, the slope. The slope is already a rate of change, right? That's what slope is a rate of change. And the rate of change is changing. That's what we're talking about. That means we're talking about the derivative of the derivative. The second derivative. We're talking about how the slope, which is the rate of change, is changing. The curve y equals x cubed is concave down to the left of the origin and concave up to the right of the origin. The curve lies below the tangents when it is concave down, and it lies above the tangents when it is concave up. Does that make any sense to you? The curve lies below the tangent lines when it's concave down. And the curve itself lies above the tangent lines when it's concave up. So you got something like this, concave down doesn't hold water, concave up does. And that's what it's changing from to, okay? And that's all about the second derivative. The second derivative is a discussion of concavity. I know, yeah, it looks like somebody in Hawaii. Yeah, I know, kind of weird. All right, take a look at the very bottom. It says, if a function y equals f of x has a second derivative, sometimes they don't, but if it has a second derivative, then we can conclude that y prime, talking about the slope, the first slope, increases if the derivative is positive, second derivative. And the first derivative decreases if the second derivative is negative. You may want to refer back to that phrase. Anyway. Take a look at example 2 now. It says, use the concavity test to determine the concavity of the given functions on the given intervals. Concavities. Okay, so we got y equals x squared on the interval from 3 to 10. Just from 3 to 10, that's kind of an arbitrary, strange looking interval, but that's what we're going to go with. What's the first derivative? This is easy. 2x, and what's the second derivative? 2. What did we just read? When the second derivative is positive, it's concave up? Yep. So where is this curve concave up? What? Where is this curve concave up?
Always.
Everywhere. Exactly. It's concave up everywhere because the second derivative is always positive. And besides that, you know what this thing looks like. It looks like this all the time. It's concave up everywhere. It holds water everywhere. The curve constantly, the curve is always above the tangent lines. So it's concave up. You with me there? It's not that hard. When the second derivative is positive, the places where the second derivative is positive is places where this thing is concave up. And the second derivative is always positive, so it's always concave up. I know that was probably too easy that it made it confusing. But the second one that they've got in example 2 is 3 plus sine x from 0 to 2 pi. On this interval from 0 to 2 pi. That's all the only place we're looking. You probably have a pretty good idea of what this thing looks like too. It's just a sine curve that's been moved up 3. So it's going to start at 3 and it's going to go up to 4, down to 2, and back up to 3. Right?
Yep.
And you may have a good feel for concave up and concave down. Think about that. I mean, the curve's going to go like this from 0 to 2 pi. So it's going to be concave up from here to 2 pi and concave down from 0 to pi. You can see that. And you should check that out with graphs. I mean, I'm not going to restrict you on your calculator at all, but let's see what happens with the math. What's y prime? Cosine x. What's the second derivative? Negative sine x. What quadrants is sine positive? First and third, but this is now negative. First and third? First and second? I thought I heard first and third. First and second. Sine is positive in first and second. So this particular derivative is negative in the first and second quadrant. And a negative, negative, or positive in the third and fourth. Well, here they are. This is the first, this is pi halves. This is 3 pi halves. When you break right there, we've got concave down. In other words, this is negative in the first and second quadrants. So it's concave down. And it's positive in the third and fourth. It's concave up. Okay? And we knew that from just looking at the graph. But if you take a look at the graph that they have to in the green, I'm talking about right here. For those of you watching, oh crap. For those of you watching here, I'm talking about this graph right here. If you look at that thing right there, what they've drawn for you is the actual function in black, and they've drawn the second derivative in red. And the second derivative is negative until you get to pi, and positive thereafter. That's what you're looking for. Not whether the red thing's concave up or down, but whether it's positive or negative. Because what they've drawn is the second derivative for you in red, and you're looking for positive, negative stuff there to decide concavity. You following? Getting the idea here? Okay. All right. Here's a nice thing. What happens as it changes concavity? What do we call that? Well, in the first derivative, when it changes from going up to from increasing to decreasing, we call it a max or min. When it changes from concave up to concave down or vice versa, we call this point right here an inflection point. Okay? An inflection point is a point where the second derivative is equal to 0. And that's where we look for a change in concavity with another sign chart. Okay? So when we take the second derivative and set it equal to 0, we're looking for inflection points. But we may or may not find one, but this is the only place we can look for inflection points is where the second derivative is equal to 0. And the second derivative, this sign right here, would be equal to 0 at pi and 2 pi. If you'll remember where sine is 0, sure enough, at pi, that's got an open interval there, so we don't check at 2 pi. But at pi, it's actually equal to 0. And it is concave down before it and concave up after it. Therefore, pi is an inflection point. X value or inflection point occurs, at least.
So does it have to be concave down, concave up, or just has to be a switch?
It has to be switching from one to the other. If it's an inflection point. Not all critical values of the second derivative, not all of them will provide an inflection point, but it will provide a place to look for one. Okay?
Okay.
Yeah, and it's just a change from up to down or down to up. All right, moving on. Example 3 says, find all the points of inflection of the graph of y equals e to the negative x squared. This is a very, very special function, this one. E to the negative x squared. I won't tell you why it's important today. It'll come up again later, but we're gonna play with it for today. Y equals e to the negative x squared. Now, what are we supposed to do with this thing?
Derive it.
No, we're supposed to, ultimately, we're supposed to find
Points
of inflection, which means we do need to derive it. And then what will we do then? Derive it again. Yes. Y prime is going to be what?
e to the negative x squared times negative 2x.
Do you agree with them?
Yes.
Okay, I'm going to rewrite it so that we have this in the front like we're used to seeing it. That's y prime. What's y double prime? What do we need to use? Yes, right there is the product rule. First times the derivative of the second, which is this.
Yep.
Plus the second times the derivative of the first. Is that okay? Riker, you all right on that?
Yeah, I'm good.
Oh.
Think about it.
Oh, okay.
Big.
So, we got to set this thing equal to 0. That looks pretty nasty. Okay. So if I set this thing equal to 0, that looks just awful. What do you want to do then? Because the calculus is over and the algebra is ready to destroy you, right? Okay. Don't succumb. What do we do?
Multiply the negative 2e to the negative x squared by the negative 2x.
You want to multiply this times this?
Yeah.
All right.
Take out an e to the negative x squared.
Can I take out a 2 along with it?
Yeah.
Take out a 2e to the negative x squared out of both terms, and what will that leave us?
4x squared or 2x squared.
2x squared.
Minus
Minus 1? Now what?
I'll set each of those.
Each of them gets their shot of being 0, right?
Yep.
Okay. 2 will never be 0, so I can ignore that. When will this be 0?
When x is 0.
E to the 0 is 1.
So whatever.
Never.
Never.
It might be not as clear, but e to the x, for example, folks, e to the x is never 0. But what about e to the negative x squared? If you're not quite sure of that, you might want to check that out. Get your calculator and check that out. Find out if you can see where that thing crosses the x-axis. That's a way of investigating its zeros. Just do the e to the negative x squared. That's it. Just graph that and see if it's when it's 0. It appears to be 0 in a lot of places, right? But do you think that thing is kind of asymptotic? Ask it. Ask it. Say, what's the value of this thing when x is 10, for example?
Pretty small.
Pretty darn small, but not 0. Ask it what it is when x is negative 10. Same value, right? Always positive. Asymptotic, never 0. Okay, so this one will never be 0. When will this one be 0? So we say, can we do this without doing much of the algebra? X squared is equal to 1/2. You okay with that? So x is going to be plus or minus the square root of that, which is root 2 over 2. Is that right? Now that's something we recognize in trig, but there's no trig here. Still, root 2 over 2 is a place where this thing is equal to 0 and a place we need to look for inflection points. So We put it on a sign chart, just like we did with the first derivative. And find out if it changes sign. Because if it changes sign, we've got inflection points there. Can you think of something to the left of root 2 over 2 that would be nice to plug in? Did I hear negative 30?
No, I said -3.
Oh. I was going, yeah, negative 30 would work. But so we plug in -3. Shh. We plug in -3. And what will happen if I plug in -3 to this part? It has to be positive. We already agreed this was always positive, right? Plug it in here, we're going to get a positive times, if we put a -3 in here, we'll get a positive, right? Now, since this is the second derivative, and I should have put that here, y double prime, I realize we use y's over there and f here, but if we plug this in here and we get a positive here, we don't write increasing, we write concave up. That's what we've determined here. Okay? If we plug in 0, that's a nice thing to plug in here. We're going to get a positive times a negative. So we have concave down here. And if we plug in a positive over here, a +3, we're going to get the same thing that we got over here when we plugged in 3 here, because the only difference is it's going to be squaring it. So we can have a positive times a positive, and that's concave up. So do we have inflection points?
Yeah.
Here's what's going to kill you on the quizzes and the tests. When it asks you to find inflection points, people list negative root 2 over 2 and positive root 2 over 2, and those are only the x values.
Gotta find the y's.
Inflection points are points. How do we find the y values? Good, but you plug it in over here. What is E? Try and figure this one out. What is E to the negative root 2 over 2 squared?
That's the square root of e. 1 over square root of e.
Yeah, it is. When you square this, you get 1/2, don't you? I mean, we square rooted 1/2 to get this. So if you square this, you get back to 1/2, right?
Mhm.
So this is 1/2. So it's e to the negative 1/2, which is 1 over root e. What happens when you plug in negative root 2 over 2 in there?
-1 over root e.
No, you get the same thing
Because it's squared.
because you're squaring it. Doesn't matter whether it's positive or negative. So both of these points on it are up the same amount. And if you look at the graph, finally, look at the graph that they have for you on the bottom of page 208 on the left, you can see that they have the same height. Because this is an even function. Remember what even means? Y-axis symmetry. So the two inflection points are up the same height because they occur at positive and negative the same thing. So since it's an even function, that's what happens. We didn't make that point before. It's okay.
Does it matter if we, like, you have a 1 over the square root of e, and book has it as a decimal? Doesn't matter.
Doesn't matter to me. Okay, ready to move on? Catch all of that information there? Sign charts, when you do the second derivative, do not produce increasing and decreasing. It's concave up, concave down. And when there's a change in concavity, you have an inflection point. That's what we were asked to find. All right, example 4. Example 4, you need to look at the graph and you need to have a sticky note on the one below it, right? Don't be looking under there yet. It's like an advent calendar. It's fun for this time of year. Here's what it says. It says the graph of the derivative. The graph of the derivative of a function f from -4 to 4 is shown. Here's the questions we're going to answer. Answer the following questions about f, justifying each answer with information obtained from the graph of f prime. Remember, we are looking at the derivative, not the original function. Get that in your head. We're looking at a graph of slopes. Slope values, okay? A, on what intervals is f, the original function, on what intervals is it increasing?
Negative unity to 1.
We're only considering it from -4 to 4. There are no infinities on this. And we have to be careful with that on the next quiz too, because if it only says it's defined on -4 to 4, and you write infinities in your answers, you're gonna miss it, because we're only considering from -4 to 4 in this one. So, where is it increasing?
-4, -2.
From -4 to -2, and then? Is there any other places?
-2 to 1,
Okay,
and then the rest of it is decreasing.
all right. Riker thinks it's increasing from -4 to -2, and then from -2 to 1. Would any of you buy the idea that it's increasing from -4 to 1?
Yes.
Because it doesn't increase or decrease at a point. That's okay. Either way, it's fine with me. I don't care whether you leave the -2 out or include it, it doesn't matter to me. Okay? But why do you believe that? Why do you think that's the case?
Because that -2, it's not increasing or decreasing.
Okay, now I'm done with the discussion at -2. Why do you believe it is increasing from -4 to 2? Or from -4 to 1?
Because this is the graph of the derivative, and if the derivative is over the x-axis, then always increasing.
That was a cumbersome way of saying who else wants to describe it.
Positive.
Yep.
Yeah, it's positive. That's okay, Riker. Riker, you were correct, but that's, yeah, okay, all right, because it's positive. All right, on what intervals is the graph concave up? Okay, watch it, folks, this is the first derivative we're looking at. On what intervals is the graph of f concave up?
0 to 0, 3 to 4.
Who said that? Parker?
What is that?
Did Parker say that or Devin?
Devin.
Tell us again what you think?
-2 to 0 and 3 to 4.
Strange decision, why do you believe that?
Because that's when the slope is positive.
The slope of what?
This first derivative, second derivative. The first derivative.
Because the second derivative is all about slopes of the first derivative. Isn't it? You take a derivative of a derivative, it's about slopes of the first derivative, and he's claiming that, he's claiming that the slope of this thing we're looking at, which is the first derivative, the slope is positive from -2 to 0, and again from 3 to 4. Ooh. Okay? Y'all understand that decision? Because that's correct. All right, so remember that when you're talking about things, if you're looking at a first derivative and you want to make decisions about the second derivative, you need to look at slopes of the first derivative.
So, is it -2 to 0 including them, or is it like excluding
Again, it
them?
doesn't matter. It doesn't matter. Nope. All right, next question. Is everybody okay on that decision and how that was made?
Yeah.
You sure? Okay. Part C. At which x coordinates does f have local extrema? At which x coordinates does f have local extrema?
-2, 1, 4.
-2, 1, and 4?
Yeah.
Anybody disagree with that? I do.
0.
I do too.
I think that there are extrema only at 1 and 4.
Oh, so it's gonna be a shelf point.
Yeah, -2 is a shelf point because there's no change in sign.
So,
There's no change in sign in the first derivative at -2. Okay? If I asked you to make a list of critical values for the first derivative test, then you would say -2, 1, and 4. But you will only find maxes and mins at 1 and 4. You agree?
I do.
All right, be careful with that. Part E, part D. What are the x coordinates of all inflection points of the graph of f? Inflection points.
-2, 0, and 3.
I agree.
The zeros of the first derivative, in other words, the places where the first derivative is flat, changes in sign in the slope of this graph, changes in sign in the slope of this graph, make inflection points for the original graph, because when you have a change in sign of slopes of the first derivative, you have this kind of thing going on, concave up and concave down changes. So we do have inflection points at -2 and 0 and 3. Y'all see how we identified those? Okay, here is what we're gonna do. With all of those things we just learned, and the things that we concluded, we're gonna sketch a possible graph of the original function. Based only on its first derivative, we're gonna put the inflection points in, we're gonna put the maxes and mins in, all those things. See if we can draw a graph of it. Okay, on the interval from negative, and by the way, I'm not going to put a y-axis in here. I'm only going to put an x because we have no idea where it is, y-wise, right? So I'm just going to put an x-axis on this thing. I got a 0 here, negative 4, 4. I'll split these up. Okay, so how shall I start over here on this left side? How shall I start drawing? What should I do first? What's it doing? Before something interesting happens, what's it doing from negative 4 to negative 2? The original graph.
It's increasing, but
Increasing concave down.
Yeah.
So from negative 4 to negative 2 is
Increasing concave.
increasing. How do you know it's increasing?
Because the first derivative is positive.
What's positive?
First derivative.
First derivative is positive, but the first derivative is decreasing.
Yeah.
So that's why you're saying concave down. We got a slope that's negative on this thing, but the values of it are positive. Okay? So concave down, increasing but concave down. Like that. Would you agree?
I would agree.
What happens at 2? I mean at negative 2. Oh, wait a minute. I gotta go over here. Sorry. This is negative 2 here. So from negative 4 to negative 2, it is going up but concave down.
Yep.
Do you all understand that decision? Then what? What happens at negative 2?
It's got a shelf point. Shelf point.
Shelf point. Is there any change in anything that's going on so far?
Yeah, just to concave up.
Goes to concave up.
Yep.
But continues to increase.
Yep.
I'm going to bring this down a little bit because I'm probably not tall enough to do all of this. I'm going to come down here. So you're saying that it continues to increase. What about the values? Are the values positive or negative? We can't tell. We can't tell. And it increases, so it's changing its concavity right here and increases to where? Where does it stop increasing?
0. Well, 1. Well, technically
1.
but it stops being concave up at 0.
So we're going to increase until we get to 0 and be concave up.
Yep.
Is that right? Okay. That's not a very obvious concave up, but what's what we're going to do? Concave up right to there. And then what?
Goes concave down, but still positive.
Concave down.
Concave down, but still going up
Still
Going up to 1.
till we get to 1.
Yeah.
It's concave down there. Still increasing, I think, isn't it? Is it 1? Does it stop increasing and start decreasing? So I'm concave down to there, and so right there is probably going to be a maximum. Do you agree? And then what will it do?
Concave down.
Concave down and decreasing until where?
4.
Until decreasing till 4.
But it's concave down. It's concave down. It's concave down until 3.
Concave down until 3.
Yep.
And then changes concavity but continues going down
Uh-huh.
till it gets to 4. Something like that. This isn't a really obvious change in concavity, but it happens right there. Okay, check it out and see if that has about the same shape, has about the proper shape. Is that what it looks like? Does that kind of look like that?
Yes.
Boom.
Kind of looks like that. Okay, put that back on for the next person who has your book. Is it still sticky? If it's not, let me know. I'll cover it up with something sticky.
Yes.
So those kinds of things may slow you down a little bit because you have to consider 2 things at once. Your mind's toggling back and forth between concavity and increasing and decreasing. Consider them slowly and try to draw it. And keep in mind that the y values are non-restricted. Y values could be anywhere. Ours was down a little bit, but it had the same shape as theirs. That's what we were after. Okay? I'll leave that on there for a second. Okay. Continue on down past that example 4. He gives a little caution just below where that example ends. He says, caution, it is tempting to oversimplify a point of inflection as a point where the second derivative is 0. But it can be wrong for 2 reasons. The second derivative can be 0 at a non-inflection point, just like a shelf point can be at a point of, a critical value, because it will produce a maximum min. So that can happen with inflection points too. It just gives you places to look for them. In part 2, it says the second derivative need not be 0 at an inflection point. What? It might be undefined. You look for inflection points in the same places, or the same way that you look for critical values. You find the second derivative, set it equal to 0, and find where it's undefined. And all of those are places to look for inflection points. Okay? All right, let's continue. Example 5 says, a particle is moving along the x-axis with position function 2, it's a nice polynomial. This cube polynomial says, find the velocity, acceleration, and describe the motion of the particle. Don't turn a page. Did everybody come in? I only have 3 there. Somebody didn't come in. Who was it? We got Sam, Micah, Genesis. Did you get a note, Genesis?
No, I checked the library.
Oh, everyone's here.
Sweet, thank you.
Okay. Okay, don't turn the page. Here we go. Somebody read that to me. And notice that it's x of t. It's only because the particle's moving along the x-axis as a function of time. So it's not like we're messing things up. It's going horizontal. What is it? T what?
2t to the third
Oh, 2t. Hang on. 2t to the third.
minus 14t squared plus 22t minus 5.
Okay. What are we supposed to do? We are supposed to find the velocity and acceleration and describe the motion of the particle. All right. So velocity is going to be x prime of t, and that's easy. What is it? I know this is boring. Just read it to me fast.
60 squared minus 19 plus
And what is the acceleration?
14 minus
So the acceleration is not a constant. This isn't gravity because this thing's moving horizontally. Something's propelling it. Something's moving it around. So we've got our position, velocity, acceleration. And so we found those. And then it says, okay, now describe the motion of the particle. What? That seems like a difficult, daunting task. How do we describe the motion of this particle?
We're gonna need to find critical points at velocity and acceleration.
Okay, if I find the critical values of velocity, what will that tell me?
Maxes and mins.
That'll tell you, yeah.
With respect to the particle moving around, what will it tell me?
When it changes direction.
When it changes direction, exactly.
Yeah.
Okay, so let's set that one equal to 0. I'll go ahead and do that in here. 6t squared minus 28t plus 22 equals 0. Does it factor?
Yeah.
Let's take a 2 out at least. Three and 11 add up to 14. So there's a good chance it factors. 11 here, 1 here. That gives me 3 plus 11 is 14, both negative. So t is 11 halves or 11 thirds and 1.
Sure. Yep.
Sure, and the 2 just disappears.
Oh, you people.
Yeah,
Well,
the
the
2
2 can never be 0.
2 will never.
Oh,
Yes.
Brandon, you work.
So there are critical values at 11 thirds and 1. Is that right? Oh, I always want to make a pie out of things that look like 11s. 11 thirds is above 1. Hang on a minute. Okay, so we're going to check this velocity, which is the derivative of position in each of those regions to find out if there's a change in value. Or change in sign, I should say.
Plug in 0 first.
Where do we plug it in?
The derivative.
Ah, the derivative. This is the easiest plug-in right here, in my opinion. because I get two values that I can look at separately and decide if their product's going to be positive or negative. I want to check to the left of 1. If I plug in a 0, I'm going to get a negative 11 times a negative 1.
Positive.
Okay, so this is positive, and it is so that it is increasing here. I'm doing first derivative test. Between 1 and 11/3, should we try a 2? Will that work? 2. That'll give me 6 minus 11, which is negative. 2 minus 1, which is positive. So this is negative, and so it's decreasing. Checking above 11/3, like 4. That'll give me 12 minus 11, which is positive. 4 minus 1, which is positive. And so it's increasing. So we have a maximum and a minimum here. Right? What does that mean in the context of the problem?
That's where it changes direction.
Okay. What was it doing before it got to 1 and changed direction? Which direction was it moving? To the right, because the velocity was positive there. So when we start, but it was moving right as it was approaching 1. It was moving right, changed directions, went left until we got to nearly 4 seconds, turned around and went right. That make sense? Okay. Acceleration. What's that going to look like? We got to set the acceleration equal to 0. Where's acceleration going to be equal to 0? I'll do that over here. 12t equals 28. T is equal to 7/3. And if I line these two things up, where will 7/3 be? Over here, in there, or over in between, or out there? In between, about right here?
Yeah.
Okay, so that was the only critical value I got. So what's to the left of 7/3? We're talking acceleration here. I didn't factor anything, so I just got to plug it in. If I plug in something to the left of 7/3, like 0, I get a negative, right?
Yep.
Which means what?
Concave down.
Concave down, or in other words, well, anyway. Okay, and to the right of 7/3, like 4. I get 48 minus 28, which is positive, right? Concave up.
Yep.
So who would like to take a stab at telling me how this particle is behaving as it moves along using both of these charts?
Goes right until 1, and it starts out fast and then slows down. So that's sort of right.
Well, maybe.
Great, keep going.
Then it goes left.
Where is it? Where? Okay, instead of going fast, instead of those words, talk to me about speeding up and slowing down. Remember, speed just means it's the absolute value of velocity. So without regard to sign, speeding up and slowing down in whatever direction it's headed. Can you talk to me about that?
Yeah, Lenny, you're good.
I think that concave down would mean it starts out pretty fast because it goes like whoop.
Yeah.
So it starts out fast and slows down once it gets.
Where does it start slowing down?
At 7/3.
Slow down.
What is it? Okay, here's the question. What is the particle doing? What is the particle doing from here to here?
So it's going to the right, but it's slowing down because it's going to have to change directions at 1.
So it's moving right, but slowing down in this region of stuff right here.
Yeah.
Okay. What's it doing right here?
It's moving left, but it's still going.
slowing.
But it's speeding up. It's starting to speed back up.
It's now moving left
Yeah.
because it changed direction right here.
Mhm.
And so now it's going left and
Speeding up.
speeding up. So I'm just lopping off these places right here. Speed, you think it's speeding up, and then what's it doing from here to here?
Still going down, but it's slowing down.
It's going left, is it?
Yeah.
It's going left, but
Slowing down.
slowing down, and then what happens right here? Changes direction, and then what does it do from then on?
Speeds up.
Speeds up. For those of you that missed that entirely, memorize this. It's not hard to memorize, it makes good sense. And when you have both sign charts together, you're talking about something in motion, whenever the sign of velocity and the sign of acceleration are the same, it's speeding up. If the sign is positive here and negative here, right there, between right from here to here, the sign's positive and negative, it is slowing down but moving forward. It still tells direction. Now, in between here and here, this is negative, so is this, still negative, which means it's speeding up. When the signs are the same, it is speeding up to the left. You following me? Then from here to here, we've got positive down here and negative up here, which means it's still moving left because velocity still tells you which direction it's headed, but the signs are different, so it's slowing down. Then right here, it changes direction again. It turns around and goes right. And after that, the acceleration and velocity are both positive, so it is speeding up to the right. That's how you describe its motion. Okay. If you turn the page, I have these for you. I don't know if it will help you at all. You're welcome to do whatever you want with these papers. It's not required or anything like that. But I gave you, I've made a copy of this so that you could write down things that are in that you want to help you remember this little fact. These are the graphs of the things we've just been discussing. The first one is the original function. Even though they graphed it horizontally, vertically, it was kind of bad that they did that. You guys are smart, you can handle it.
No. That is so smart. What are you talking about?
Notice how all of the graphs are lined up. They not only have the graphs lined up, the x-axis and stuff like that. If you draw lines where interesting things happen, perhaps you can convince yourself what to do. This is the function. This is the. I know the things that went along the x-axis, but they did its position along the x-axis, graphed along the y. You'll get one of these, Jeff. So they're going to graph position along the y right there, even though it's moving along the x-axis. I know that's a bummer. But what you want to do is lop off places where interesting things happen, maxes and mins and crossings of the x-axis and things like that. Make little notes to yourself about what's going on. It's all written down for you, and you can see that the author on the next page, on page 210, made those two sign charts just like we did. He compared what was going on. In regions where it was pink, it was speeding up. Wow, that's a lie. Where the pinks overlap, where both of them are pink, is speeding up. Where both of them are blue, is speeding up. But the sign on the velocity determines which direction it's going as it does this. Okay, that's all the discussion we're going to have on that. I made all kinds of notes to myself on that. But the main thing is, if you can draw sign charts that line up so that you get these critical values where they belong, then in places where the sign of the first and second derivative are the same, the particle is speeding up. When they're different, it's slowing down. All right. Moving along here. On page 210 at the bottom. We're switching gears here a little bit. You know this. You've learned this before in pre-calc. We also discussed it in algebra 2. The growth of an individual company or the growth of a population in sales of a product or of salaries often follows a logistic or a life cycle curve, like the one shown at the left. Take a look. Page 210 at the bottom. Life cycle curve. Okay. For example, sales of a new product will generally grow slowly at first, then experience a period of rapid growth. Eventually, the sales growth slows down again, and the function f in figure 430 is increasing. So it's increasing the whole time, but it's increasing faster before the point of inflection, and it's increasing slower after the point of inflection. Okay. Its rate of increase, f prime, at first is increasing because it's concave up, and then decreasing because it's concave down. But it's still increasing. That happened with the iPhone. That thing was first invented and gave a challenge to other types of phones that were out there. The growth was exponential. But now everybody that ever wanted an iPhone or has been intrigued by one has one. And so sales are very, very steady. They're still quite high, but they're very steady. They've got some loyal followers, but we don't have everybody in the world trying to get their hands on one. Okay? Some graphers have a logistic curve, and we do. Ours has a logistic curve thing built in as a regression model, and we use this feature in example 6. Okay, so grab your calculators because you've got data, and you have to fit a curve, a logistic curve, and so put the data in there. In the stat function of your calculator. Oh, are those commas, not decimals? I keep not having glasses on.
No, they don't.
Was it commas?
Yeah.
Oh, good. Just probably watching this.
All right, let's go build us a window. I'm gonna go from 0 to 120, tens. I'm gonna go from, let's say, 40,000 to 1,000,000. 500,000. Oops. Equals, put those out, and plot on. You able to get a graph? Looks like that, your points? Something like that? Can you see that feels a little bit logistic? Starts out at growing exponentially and then kind of starts to flatten a little bit. Okay, so it says, find the logistic regression for the data. Go back to stat, over to calc, and down to, way down there, the very last one called B, logistic. This one was to, go. It'll take it a minute.
Staff count.
Oh, I didn't do that one.
And then you go all the way down to interesting. And then you
Oh, I wanted my diagnostics on. How many of you don't have diagnostics on? Does it have an R squared value on the home screen? No? Okay, follow this with me. Go second, and the number 0, that's catalog. Go down to D's, or else go alpha, inverse key, to get you down to the D's. Go to diagnostics, and go to on, highlight that, and hit enter, and then enter again. Then you can go second entry, second entry, second entry for me, and hit that again, and you'll get diagnostics for it. Maybe not. I didn't get any diagnostics, did you?
Diagnostics.
You get an R squared value?
Same thing.
Usually that'll tell you how good of a fit it is. Apparently Logistic doesn't have the diagnostics built in.
I don't know, it looks pretty good though.
Yeah. If you actually graph it, it's a pretty good fit. Okay, so just by visual inspection, looks like it's a reasonably good fit. Logistic curve. I'm going to decrease my y's a little bit more. I'm going to let them go down to negative Yeah, okay.
What is this diagnostic?
Everybody able to get a curve about like this, and visually we know it's a pretty good fit? Did anybody get diagnostics on? Did anybody get an R squared value? I don't think logistic has that built in.
No, I haven't got one of those.
That's a good fit.
This is what you should be getting probably, something like that. And we got that with a window like with that.
Other 30 more footage.
That's it. Good graph.
Are we ready to go yet, folks? Riker, what are you doing?
I am helping Boston.
All those buttons you were pushing so fast looked to me like you were playing a game.
Oh, I've been playing such a fun game called Graphic.
Okay, so it says find the logistic regression for the data. What would you write if you were actually doing this as a problem on your exercises or a test? A part says find the logistic regression for the data. What would you write as the answer to A part?
Well, you
The equation.
Yeah, see?
How do you
make it so it goes like down?
It even gives you like the same for it.
You
Things you
change
can
it
format.
on the mode, go to mode.
That's a lot of stuff.
That's a lot of stuff.
895,597.8
0.3.
divided by.
Okay, so you would write the equation. You go to y equals screen and write down that equation. And for heaven's sake, don't give me all the decimals, okay? Here's how you decide how many decimals to give, folks. Shh. You stay true to the way the population was given to you. That's what this thing's predicting. And they were whole numbers. I thought they were all to 3 decimal places before I got my glasses. So round to the nearest whole number. That's what they did. That's what you're going to do. Okay, B part. Use the regression equation to predict the Alaskan, oh, that's what we're graphing here, the Alaskan population. Use the regression equation to predict the Alaskan population in the 2020 census. When did this thing start?
1900.
1900. Years since 1900. So the first 20 we're looking at there is 1920. What are you going to put in to predict the population in 2020?
120.
Good, do that. Go second, calc a value at 120. And if your x's are not big enough, you're going to have to go extend your graph. It looks like 781,253. Okay, so that wasn't that bad. C, find the inflection point of the regression equation. Oh crap, really? Find the inflection point of the regression equation. How are we going to do that?
Yeah.
What?
That's a good idea.
What?
Graphing the derivative equation.
Okay. Inflection points have something to do with the second derivative though. Why are we graphing the first one?
So we can still find
In
everything
order to
for
get
the
the
first
second.
derivative.
Oh yeah, we learned that before, right?
Yeah.
All right, so go ahead and do that. Go to y equals, go to y2 and type in nderiv, math 8, y1, bars, y bars function y1, comma, x, comma, x, close it. Are you going to turn the first one off so you can see just the derivative, or it doesn't matter to you?
It doesn't matter.
All right, hit graph. Because they're colored, it doesn't matter. Well, that's a horrible graph. It just looks like a line with a couple of little teeny tiny steps in it, right? How come?
What if one doesn't have a graph?
Because this one is a
It's not in the same
Because the slope is a certain amount, but then our windows.
Oh, right, because we're graphing slopes, and the red line appears at the bottom on the x-axis because the slopes aren't all that great. They're not into the hundreds of thousands like we got on our y-axis, right? So if you want to study the derivative, you better go into your window and cut down those y's a lot. How much, you think? I'm gonna go from 0 to maybe 100 and see what that does. By 10. Oh, can you see it now? So I gotta think a little harder about my window. How much is, we're talking about the slope, how much has it changed from 20 to 30? 4,000 approximately, right? And then quite a bit more, so I gotta go, my y values, which are slopes. I think I gotta go a little higher, so I'm gonna go to 1,000.
Like start at 1,000 or max at 1,000?
I'm gonna let it go, I'm gonna let my y's go up to 1,000. If I let my y's go up to 1,000, I can barely see it.
Right.
That's because the population in Alaska is changing by more than a couple of thousand a year at first. Okay, and so I'm gonna go to my window and go to 20,000. There, I'm starting to see my red one. My blue one kind of took the place up here in the corner here, but my red one I'm starting to be able to see a lot more. Okay, window and think about slopes and how the population is changing, because that's what you're graphing is slopes. How come I don't change my x's at all?
Because it's the same amount of time.
Yeah.
Same amount of time, but we need to change our y's because they have different values for the slope. Okay, so C says find the inflection point of the regression equation. That's what we're out to do, and we've only got the first derivative here. Inflection points have to do with the second derivative. Do you want to do a second derivative? I would not.
Let's
No.
not do that idea.
You can, and with these faster calculators that you have, you may get a second derivative, but you're gonna have to design a new window again. Can we get the information we need from this?
Yes.
Where do we look?
When it's positive or
When the first derivative,
it's decreasing. Positive.
has a maximum.
That's what I was saying.
Listen. In the original curve, that's logistic, it goes up like this. Wouldn't you say that right here, it's growing the fastest, and that's also an inflection point,
Yes.
because that's where it's steepest. So if you have a graph of slopes, you want to know when the slope is the greatest because it corresponds to the inflection point.
Yes.
Right.
So find the maximum of your red curve.
That's one mark.
I can do too. Second calc a max of what? Now you're gonna have to move your cursor down one to get it to get on that graph. You have to go down one because it's y2.
Just like 115 or 11,553.
But at the X, it's 82.
Yeah, so it's fastest growing 82 years after
19.
So the inflection point is, what did you say? I want to show you something cool here about your calculator. Y'all found this maximum?
Yeah.
Okay, and you found it to be an x of about 83?
No.
And what does the 11,553 indicate?
That's the slope of,
What does it indicate about the population of Alaska
that's how much it was increasing per year.
at its maximum?
At its maximum.
How do we find the actual inflection point?
You go up on.
Yeah, you just go up. Because wherever that x value is here, if you go up, it will go to the other graph, even if you can't see it. And tell you where it is. So it's 82.7, comma, 44,447,792. That's the point on the actual curve. I got 793. Maybe there's a slight difference in our calculation. That's close enough. If you get to the right 100,000, I'm gonna be fine. 447. Okay, so C says, what significance does the inflection point have in terms of population growth in Alaska? The inflection point is when it was growing the fastest. D, what does the regression equation indicate? Listen, folks. What does the regression indicate about the population of Alaska in the long run?
It's still going to increase, but not as much.
In the long run, it will settle on an asymptote. If you remember your logistic curves, it will settle on an asymptote, which is the numerator of your regression curve. You remember that? The maximum on a logistic curve is the numerator. It is the asymptote that it will approach. So in the long run, Alaska will settle on about 900,000 people, according to the data we have so far. That's what you always have to qualify with. But that's the numerator. If you go to your y equals screen, the numerator of that logistic curve, which is in y1, the numerator tells you the asymptote of approach, the maximum carrying capacity, according to the data that generated the curve. That's not necessarily what's going to happen, but we anticipate it being right around the numerator, which is around 900,000. Okay? Take a look at example 7. We may not finish this, but I'm telling you guys, you got everything you need to do this assignment, even if we don't finish the exercise. Even if we don't finish the lecture. So listen up. Example 7 says, find the local extreme values of this polynomial. It's a cubed polynomial. Here's what he does to solve that. He finds the first derivative and the second derivative. Testing the critical points at plus or minus 2. Where do you get those from? Plus or minus 2. Look at example 7. Look at f prime. He says that's going to be 3x squared minus 12. He takes the 3 out, factors it. Can you see the plus or minus 2 in there?
Yep.
Okay. Testing critical points at plus or minus 2. There are no endpoints. It says we find that it has a local maximum at -2 and a local minimum at 2 using the first derivative test. What? No, that's not what it says. He used the second derivative. What? Testing critical values. What the heck's he doing there? The second derivative. It's the coolest thing in the world, especially if you're dealing with polynomials. Think about this, folks. If a second derivative is an easy thing to get, and this is extremely easy to get, then what you can do, we can figure the critical values in the first derivative, positive and -2, right? That's what we're looking at.
Yep.
The question is, at positive and -2 in the actual function, is it concave up or concave down there? At those values, concave up or concave down. So we plug in positive 2 into the second derivative, and it's positive, right? Which means it's concave up. Which means at 2, there is a minimum, because concave up things are minimums. At -2, the second derivative has a negative value, which means it's concave down there. And concave down things are where maximums occur. So you can use the second derivative to figure out whether you have a max or a min in the original function. But you have to test critical values from the first derivative. You have to plug those points into the second derivative to determine concavity, and that can tell you whether you have a max or a min. Which in my opinion is not all that wonderful, because look at that third degree polynomial we started out with. Isn't it going to start low and end high? Did we learn that? The behavior of polynomials. Well, it's going to start low and end high and turn. It's going to hit a maximum first at -2 and then a minimum at 2. So it's not that good. But it is a way of using, especially if the second derivative is very easy to come by. You can look at concavity. It's called second derivative test for maxes and mins. You can use them in conjunction with each other if you like. You should, just for the fun of it, maybe even in your next class, don't get in trouble. You should try to do example 8 without uncovering the graph. You should try to use the information in example 8. Go through it kind of like we did before. It'll give you maxes and mins and increasing and decreasing and stuff like that. And see if you can draw the original graph, given the graph of the derivative. They only give you the equation, but your calculator can graph it for you if you want. You should try it. Because I'm not going to have time to do it with you. You should try it. I don't have, the rest of it, you can look at it if you want. But example 8 is kind of fun to do. You should try it. I don't have time to do it for you. Anyway, you have all the information you need to do this exercise. Get it done over the holiday. Tomorrow I'm going to expect a report on 4.1 and 4.2, and those will be permanent. Because I got to get grades in by Friday night.
Here, how's this blank piece of paper?
What's that?
No.
If you don't want to do this, if you don't want to make notes on this, or you understand things pretty well, you can throw this away. This was just as a crutch, so you can make some notes for yourself if you wanted to. To understand the kind of notes you would make, this is the notes that I made. There's some lines and said what was going on and stuff like that. Just to solidify that concept in your mind. All right. Have a great holiday. See you, Jeff.
Go to the board then.